we need to apply Newton's second law quantitatively and also qualitatively in cases where the mass is not constant. I'll do a simple example first of all to do with space rockets. So quantitatively is to do with numerical values and qualitatively is just with description. So we'll do a qualitative description first of all. Now most of the examples that you see, the mass will be constant, but you also need to be aware when the mass is changing in some way or another. Now when the rocket goes from the side, it uses up the fuel, the mass is actually changing. How is the mass changing? Well, basically it uses up the fuel, so it gets less and less mass. So as the fuel is used up, the mass gets slightly less. So basically if the force is going to be the same and the mass is going to be less, then according to this equation we're going to find that if the force is the same, the mass is less, the acceleration will increase. That's a nice qualitative description of what happens to a space rocket, provided the fuel is ejected at the same rate and supplies the same force. So as the mass gets less, it means acceleration will increase. Now the water jetpack is an interesting thing I've seen on YouTube and so on. This is a water jetpack. This is also an application of Newton's second law. Now you know F is equal to ma. We can also represent it as A is dv by dt, or delta v divided by delta t. This gives acceleration. But we can also represent it this way as delta mv, where mv is a change in momentum. So we can say that the mass is being changed because mass is being ejected by the pump which is connected to the guy on the jetpack. So this mass is ejected with a certain speed, v, and this is what makes it work. Now let's think about this. Let's draw a free body diagram. This is the guy, and we know there's a force acting downwards. That's his weight. That's equal to mg. If he's going to stay there and there's a force acting down, well, he should accelerate. So there must be an equal and opposite force pushing upwards. And this is supplied by the water, which has been pushed down. Now his weight is 1,000 newtons. So they must be balanced by another force upwards, which must also be 1,000 newtons. This is going to be the reaction. He basically pushes down on the water, and therefore the water pushes him up with the same force. Now let's say every second this pump pushes down 50 kilograms of water, but it depends on the speed. At what speed must this water be travelling at? Let's see the equation on the left. We've got the force, which is 1,000, is equal to 50 times by the velocity, because remember it's per second. So 1,000 is equal to 50 times v. So the speed of the water must be 20 meters a second.